Thank you, Ralph. I always wish that my mom could come and hear these things. These introductions, they're wonderful. It's great to get a chance to speak to you. Thanks for coming out on an evening. I know that physics isn't always the draw for people in the evening. I was looking at my slides over there, and when I was a graduate student, they taught us never give a talk with a question as a title. And I didn't realize until now that I made that a question. What is it and what does it discover mean? And the reason that they gave us that rule was in particle physics what's known as Hinchcliffe's Theorem. And Hinchcliffe's Theorem is if you see a science paper whose title is a question, then the answer is always no. And the way as a graduate student I learned that was there was a paper that went around whose title was, Is Hinchcliffe's Theorem True? So it drove it home pretty quickly. So I'd like to talk about the Higgs boson, the only particle named after a person, Peter Higgs, who's in the picture. And for those who are not following particle physics, anything ending in on is a particle, an elementary particle, electron, photon, they all end in on. But then to confuse things, they're often divided into categories. And so boson and fermion, all particles are either bosons or fermions. And it's to do with their spin, and more importantly, the ones that are bosons are the ones that you think about in terms of mediating forces. So a photon is a boson, and it mediates the electromagnetic force. And so the Higgs boson is just telling you it's a particle, and it's one of these ones that can mediate a force. The other ones are called fermions. Like electrons or fermions, they don't mediate forces normally. So I'd like to talk about the Higgs boson, there was a discovery this summer, and it may be that. And so I'd like to tell you about the story of what they hope to have discovered and what it might mean. And it's not completely clear yet what it means, but I hope to tell you what we should know within the next year, and what we also think there'll be things we don't know. And so it's an exciting time for us because for people my age, we've been around. A new particle like this hasn't been discovered since. Depends how you count. There was one that was discovered in the 90s, but it was one that everyone knew was going to be there. And so it wasn't really a surprise. And this is like that a little bit. It may not be a surprise, but they don't happen very often. And so it's a very exciting time in particle physics because of that. So the way I'd like to tell you the story is to tell you about the machine in which they made the experiments were done. Very impressive experiments. I'm not an experimentalist, I have to confess. So I'm just here kind of stealing the glory. But it's very impressive. Decades of work have gone into these experiments. And the accelerator at which the discovery was made is called the LHC, the Large Hadron Collider. So hadron, again, it's large, it's big, you'll see. Hadron Collider means the things they're colliding are hadrons. Hadrons are, again, one of these categories. It's not a particle. Particles are, you'll see later on in the talk that particles are also, besides being bosons or fermions, are classified according to which forces they take part in. So the strong interactions are the interactions that hold nuclei together. And so if you take part in the strong interactions, you're called a hadron. If you don't, you're called a lepton. And so what they collide here are protons, which are hadrons. And so they call it the Large Hadron Collider. And it's collider because they collide them. They collide them into each other to look for what they're made out of and what things are, what the constituents of matter are on the smallest scales. Then I want to tell you about, I want to set up the Higgs particle. So I want to tell you why you might have been, why people were looking for it, the Higgs particle, what it is, what its motivations are. And that's done in the context of the Standard Model, which is a theory that's been around for, I guess, 30 or 40 years now. It's very successful, but it's failing in its details. And so that was the paradigm that was being tested and in which the Higgs particle arises. And then I want to tell you about the events of this last summer, which in July 4th, there's an announcement at CERN, which is the lab where the Large Hadron Collider is situated in Geneva. And I'll tell you what they found. And the question that everyone's asking is, have they found the long-sought Higgs particle? And by this point in the talk, you'll know what that is, so we'll be happy. So let's get started. So what about the Large Hadron Collider? What is it, and what are they trying to do? So there's the basic idea is you're taking protons, the things, hydrogen nuclei, and they're accelerating them to very high speeds and in a large ring, which I'll show you a picture of in a second. And the idea is to collide them together at very, very high energies. And so I want to tell you about the machine, and I want to then tell you about recent events. So that you probably heard several years ago that when they started this machine, they broke it almost immediately. And I'd like to tell you the story of what broke, because that's shaped a little bit the timing of what they're doing now and what they intend to do in the future. And so part of the science story that you tell is shaped by just the reality that it's a machine that was broken and not yet fixed. And so I'll tell you the story of how that happened. So here it is. This is the reason why experimental physicists like going to Geneva. And in front of that is the Large Hadron Collider. And so Geneva is over here. There's the Jet d'eau, if you've been there. Here's Lake Geneva. And the city is here, and the stripe there is the airport. And Mont Blanc is in the background. And the red thing is the Large Hadron Collider. And that's, it's big enough that you could see it from space, except you can't because it's, it's underground, so you can't see it from space. But this is the same thing. We were previously looking towards Lake Geneva from right to left in this picture. And this is showing you where that ring is. What's spectacular about the ring is that it's 27 kilometers long. And so what you do is you take these protons and you apply a force to them, usually apply an electric field. And they use old accelerators to do that, to get them going. So they start the protons off in an old accelerator called the SPS, the Super Proton Synchrotron, I think it's called. And they shoot them into this tube going in opposite directions, and they go around and around and around and around and around, tens of thousands of times a second. And they collide them at specific spots. So they're mostly moving independently, but every once in a while they're brought together where they can collide. And where they can collide, they put a detector so they can see what comes out when they collide. And the two main ones, there's a variety of them that are there. There's 4 of them in the picture here: LHCb, Alice, Atlas, and CMS. And those are all acronyms for things. And I'm going to mostly be talking about Atlas and CMS, which are the 2 kind of general purpose detectors in the talk. And the one at Atlas is kind of physically right below the lab CERN. And this dotted line here is the French-Swiss border. So this is all France on the right and Switzerland on the left. And the lab is right on the border, basically. OK, so that's the basic setup. The 2 things that you should keep in mind that's amazing about this, and I'll say more about it as we go along, is that when you have protons or elementary particles moving in an accelerator, you don't want them to hit the air. So you have to evacuate that whole tube so it's a vacuum. So that's a 27-kilometer long vacuum tube twice, because there are 2 beams. And then not only that, you know from physics classes that particles like to go in straight lines. So to get them to go in a circle, you have to apply a force, and that's done with magnetic fields. Excuse me. But the magnetic fields you need are quite strong. So the magnets they use are superconducting. So to make them superconduct, so superconducting, which makes them carry no current, or they have no resistance when they carry current. And so, but to make things superconduct, you have to cool them down to a few degrees above absolute zero. So there's thousands, literally thousands of magnets in this 27-kilometer ring, all of which are at liquid helium temperatures of a couple of degrees above absolute zero. So it's the largest cryogenic facility in the world, in addition to being in the particle physics lab. So it's really a technological marvel. So the energies, you normally think about, you want to know how fast are they being accelerated to. The way physicists think about that is what the energy is they're being accelerated to. So the design of the machine was to, each of these beams separately would have 7 tera electron volts, which is the particle physics unit for energy. Tera is metric for 10 to the 12 of anything. Electron volt is the energy an electron would acquire if it fell through 1 volt. And that's not very useful to visualize. So the better way to think about it is that 0.94 of these TeVs, these tera electron volts, is 1,000 times what you would have had if you took the mass of a proton and you turned it into energy using Einstein's E equals mc squared. So you completely liberate all of its mass as energy. Then 1,000 times that is almost a tera electron volt. And so 7 of those is what the beams have. So what you get from that is that these things are moving, and their kinetic energy is extremely high compared to their energy that's tied up even in their mass, which is not normally the situation that you encounter. So they're in a regime where Einstein's relativity is important. They're moving at almost the speed of light, just a whisker short of the speed of light. And then you collide them. And the higher energies are good because they get closer and closer to one another. They have like charges, so they repel. And so you can probe smaller and smaller distances in principle as they collide. So here's a picture of the magnets. This is looking down the tube. And the magnets all had to be put in there, and there's thousands of them, and they put on trolleys, which I'm told were, the trolleys only go 3 kilometers an hour or something like that, so they're very slow. And so it takes a long time to get around 27-kilometer ring. So the operators would often fall asleep when they're driving these things. It's one of the occupational hazards. But there's many of them, and I'm telling you, I'm beating on the magnets because that's what broke, is the magnets had a problem in them. Here's a slice through the magnets where you see the 2 vacuum tubes where the protons move in opposite directions. And so here's a kind of a cartoon of how they would collide. So one of the proton beams is moving one direction and one's the other direction, and there's specific spots where they hit each other, but they're not hitting each other all the way around the ring. So this is the lab, the CERN laboratory, and the French-Swiss border kind of runs along here, and it goes to the lab fence, and then it goes along that road. And then right underneath these buildings over there is where the Atlas Detector was that we were looking at before in the previous thing. And I'm showing you this slide because I want to show you the detectors and talk to you about what the detectors are and why they're complicated and big. And the first thing to look at in the lab here, the theorists all live down here. That's where the theory building is. But the important thing that I want you to see is that building there. That round building is kind of a public relations building in the lab at CERN. And that's the same building here. This is the people from Angels and Demons. This is Tom Hanks and Ron Howard, and I forgot her name. And you remember that? If you saw, I don't know how many people saw that movie. Who saw that movie, The Angels and Demons? A fair number of you did. If you didn't, don't worry about it. But I'm not selling the movie to you or anything, but it starts off in CERN, and it starts off at the Large Hadron Collider. And like all the Dan Brown things, eventually the church is the enemy, but it doesn't start that way. And they're after the antimatter at the LHC. And so they actually shot the first scenes at CERN. I'll show you the first clips of the movie and compare it with pictures I took when I was there. So here's the opening scene that I clipped from the movie on the internet when it came out, which is legal if I'm giving a talk. So this is don't worry about it. So the scene starts off. You start off seeing the mountains in the background, except they're in the foreground really in the movie because they wanted to emphasize for you that you're near mountains. But it's more like when you're actually there, it's like being in Calgary. You can kind of see the mountains, but they're not huge. But then the movie zooms down this vertical shaft, and there's a machine at the bottom, and this is you zooming down. And that shaft is actually there. This is a picture I took of it, and that's the Atlas Detector at the bottom. Everything that's in this thing is lowered through this shaft, and those magnets all had to go down through the shaft, and they very carefully bend them, and then they send them off in the trolleys. And along the bottom there would be where the beam is, where the protons would be going back and forth. So it starts off well, and it gets to the detector. Then the next scene is you arrive where the detector is in the movie, and then there's a glass wall, and on the other side there's this control room, and it's full of physicists, and you can tell because they're bald and they're wearing lab coats. So that's the Hollywood version of physicists. Now, in real life, the detector actually, what they've done is the background is actually what the detector looks like. It wasn't actually assembled at that point. And so if you visit the detector, it looks like that, but there's no glass wall and there's no control room there because when they're running it, it's actually radioactive. It's dangerous to be down there, so no one's down there when they're running it, least of all the people controlling it. The control room is really on the ground, and they run it by computer from there, and this is the Atlas control room full of people that look like us, and there's no lab coats in sight, and they all have reasonable hair, but it's a couple are spotty, but it's... So that's that's the setup. In the movie, they turn it on, and the particles are produced, and it's easy to tell because they all glow in the dark. And that's not true. In real life, you need these big detectors to see them because they're all invisible, and that's why radiation is dangerous, is that you can't see it, you can't smell it. You have to detect it. And so here are the two detectors the two main detectors, the general purpose ones, when they were building them. This is the Atlas one, and this is the CMS one. And what you can't get from this is the scale. And so one of these pictures should have a person. I guess you can see people there. You get an idea. That beam, that rod is where the protons will be going when it runs. And they assemble it, and they put it together so that it is hermetically sealed around where they collide. And you can see the people here are down quite small compared to the size of the thing. The same thing's true here. You might not be able to see any people, but you can kind of see the scaffolding. That's one level, and that's another level. So that's like a story. That's like a floor between ceiling and floor. And so the whole thing is like a 4 or 5 story building in height, which is kind of hard to pick. It's hard to get that in from these pictures. And that shaft you went down, think the Peace Tower. So that shaft is the Peace Tower in the Parliament buildings, and then the detector is the west block of the Peace Tower. That's the size of the thing. So it's a really monstrously large thing. And now it's big and complicated because it's hard to see these particles. And so to see why that's true, you should know something about what happens when you collide particles. Here's the Atlas Detector in a schematic, and it's got all these kind of pieces to it. And the beam is in the middle here, and the protons would be colliding right in the very center there. Excuse me. Now, there's good news and bad news about what you're doing when you're looking at particles colliding. The cartoon that you probably have heard about why people collide particles is that you should think of it as if it's like colliding cars and looking at the parts coming out, and by looking at the parts you can figure out how the car was made. And that's not quite what happens, and that's what used to happen kind of in the early 20th century, that you'd collide atoms and you'd see the pieces of the atom come out. But what happens now is not that so much. The good news is that you can collide particles, and if you're at energies that are very, very high compared to the masses of the particles involved, like they are here, then essentially everything comes out. You'll produce all kinds of particles. All the particles will come out that were not in the things that you collided, because every particle we know has an antiparticle, and it's possible to produce them out of nothing, essentially, if you have the energy to produce them. So what happens when you collide a pair of protons, like they do in the Large Hadron Collider, is that a whole bunch of things come out, many of which were not in the protons to start with. And so all possible particles that could be produced are produced. And so the good news is you don't have to choose what you're colliding delicately to get specific kinds of particles out. You'll get everything out, and colliding almost anything. And so that's the good news. The bad news is, and what makes it hard the reason for why these detectors are large is that all those particles that you produce, except for a handful of them, they're all unstable and they decay into other particles. But they decay extremely quickly in 10 to the minus 23 seconds. So even if you're moving at the speed of light, in 10 to the minus 23 seconds, you cross a nucleus, maybe. So those particles, when you produce them, don't get out of the detector, and the detector doesn't see them. They're decaying right in there where the collision happened, in the very, very middle of that detector. So what the experimentalists have to do here is what they see coming out are ordinary particles, like electrons and photons and protons and neutrons. So just garden variety particles that are the things that these new particles decayed into. And they have to be able to work backwards to say, what was it, this particular combination of protons and electrons that came out, did they come from some other particle that had been produced and then decayed in the detector? And so to do that, they have to be careful they don't miss anything. They want to identify the particles that come out, identify the directions they're moving in, identify what their energy is and everything like that, what their charge is. And the complication of the design of the detector is to accomplish that goal. They wrap it all the way around, hermetically around where the collision is so they don't miss anything. And then the various pieces here are designed to see different things. At the very, very, very center, they have set it up so that if an electrically charged particle moves through there, it ionizes things, and you can see the track of the particle moving, but only if it's electrically charged. If it's not electrically charged, then you won't see it in that central part. But in the green area there, that was designed, it's just lead and copper and things that are designed to stop particles as they move through the material. But there's not enough of it to stop all particles. An electron will stop there, say, or a photon will stop there, but a proton won't because it's more massive. It goes farther. The orange area is to stop the protons that go through the green area, and neutrons will also go through the green area to get to the orange area, and they'll stop there. And they'll measure the energy that was deposited in those areas as they go through. The blue areas are for particles that get through the inner areas, and the most important one are muons, which are, as you'll see, they're like electrons but heavier. They're kind of a particle that you don't normally encounter in everyday life, but they've been known to be around for a long time. So by comparing what parts of the detector go off, they can identify what particles came out. So for example, an electron shows up in the middle because it has an electric charge. It shows up in the green area because it gets out of the middle area and it loses all its energy in the green area, but it doesn't show up in the orange area because it's stopped already. It's lost all its energy. But different particles interact differently with matter, so other particles will go further. Photons are like electrons for these purposes. They go only as far as the green area, but you don't see them in the middle because they don't have an electric charge. So you can distinguish the two by looking at whether or not the middle part lit up or not. Protons go right through to the orange area and stop, and you see them in the middle because they're electrically charged. Neutrons are similar to protons, but they're not electrically charged, so you don't see them in the middle, but they do go through, they light up the green area and the orange area, and so on. And so by comparing all these things, muons go and they light everything up. There's a kind of a particle which doesn't get detected at all called neutrinos. There's three kinds of those. They interact very weakly. If they come out, you don't know that they've come out. You have to work backwards to see that they were there, because the way you tell if a neutrino came out this way is that all the other particles might go out that way, say, and there's no way they could do that and conserve momentum if something else hadn't gone out the other way. So it's always a case for the neutrinos that you have to figure out what you didn't see based on conservation laws. So neutrinos, you might not have heard about neutrinos, but they're bombarded. You can tell that they're very weakly interacting because we're constantly being bombarded with them from the sun. They're being produced by the nuclear reactions that make the sun shine. And there's 10 billion of them going through every square centimeter every second at the surface of the Earth coming from the sun. And the fact that you don't know that shows you how weakly they interact. They're really very, very weakly interacting things. You need light years of lead is the famous thing to stop them. So that's the idea. These particles, ordinary particles, come out, and you try and figure out what produced them. So here's a picture of an event, and it shows you how it works. There's the two blue lines in the middle are two electrons that came out, and they lit up the middle part, but not the outside part. And then these two longer lines are muons that came out, and they lit up everything, including these muon detectors on the outside. And so when they look at an event, they're looking at a picture like this, where they're seeing how the different parts of the detector graphically were illuminated by the particle that came through. So the biggest thing that the angels and demons got wrong is that when they turned on the LHC, it worked. In real life, it didn't. They turned it on, and it worked for a couple days, then it broke. And so I want to tell you about the event and how that happened. So the event happened in this picture where Geneva's at the top, and the airport's over there, and the CERN's over there. This is where the incident happened. What happened was it involved the magnets. So let me tell you about something about the magnets. So here are the pictures of the magnets before they were put down into this tube. There's thousands of them again. They're superconducting. They have to be at a couple degrees above absolute zero of temperature in order to superconduct. And they have to be superconducting in order to not have resistance as you run the electric currents through them that make them magnetic. Resistance dissipates energy, and there's lots of energy that you'd be dissipating if they had not been superconducting. Now here's the join between these two magnets. They have to all be connected to each other. The vacuum system has to go through, the electrical system has to go through. It's a complicated thing. And in particular, in there is this copper bus bar, that thing there. And it's welded together. And you can kind of see in retrospect, some of them, the welds weren't very good. This is an X-ray of the bus bar. And you can see that there's gaps in the welds. So that bus bar doesn't conduct electricity as well as it could have done. Now, you might have thought that if it's a copper thing, we make wires of copper, that's probably the thing that's carrying the current in this thing, the electrical current, and that's actually not true. For a superconductor, copper is like an insulator. It's like rubber. It's something which it conducts electricity. That's why we use it for ordinary wires. But for superconducting wires, a superconducting wire has no resistance, whereas copper wire has some resistance. And so a current, given the choice, will go down the superconducting wire. And as far as it's concerned, copper is an insulator. It doesn't conduct electricity. The reason they use it as an insulator here is that if for some reason your superconducting wire stops superconducting, you want someplace for the current to go which is not too dangerous. And so the idea would be that it would go into the copper, which can carry the current with some resistance, and it would only have to do that until the current stopped. Because if your magnets are no longer superconducting, you're not going to be continuing to run the machine. So in the schematic, if the red thing here was a superconducting wire, and the yellow thing is that copper bus bar, and the thing in the middle is the join, things are great. The current is being carried by the superconducting wire, and you don't care about the copper unless something goes wrong with the superconductivity of the magnet. What's supposed to happen is if the magnet quenches, which means that for some reason its temperature rises so high that it doesn't superconduct, the current's supposed to go into the copper, and then it carries off the energy without doing any damage. Now, if you have a bunch of bad welds there, everything's fine as long as everything's superconducting, because the current's still going along the superconducting wire, and you don't care about the fact that it's going to be hard for the current to get from one magnet to the other. So what happened was they turned on the LHC, it worked fine for a couple days, but then at some point one of the magnets quenched, so it was no longer superconducting. The current tried to go into the copper bus bar, and it couldn't, because it couldn't carry a current, because when it got to the next magnet there was a bad weld. And so the current had to go somewhere, and so it destroyed the magnet, because it had nowhere to go. So here's a picture of that. It's I'm told that this is not as bad as it gets, and it's hard to find pictures of the damage at the LHC, because if you Google damage at the LHC, what you'll find is a whole bunch of websites about how the LHC is going to destroy the Earth because it's going to make black holes, which are very good websites. You should actually all go see them, because there's a lot of good production values. There's actually movies of the Earth being eaten by a black hole. It's much better than the CERN website. I mean, in that discussion, one of the two sides has more time than the other. And so but it's hard to get pictures of the real damage. But I'm told that these things are bolted into the concrete, and it's like the magnet was picked up, moved over, and put down again. And of course, they're all tied to each other. So the next one went over, and the next one went over, and the next one went over, and so there was it was a bigger deal than they had expected it to be. And then on top of that, you have these tubes that were supposed to be vacuum. They're evacuated, so there's no air in them, so the protons don't hit anything. And of course, now a whole bunch of crap goes down those tubes because you've broken the vacuum. And so this is a picture down those tubes where copper normally would be pink, and all the gray stuff is just crap that's gone down the tube, and it's all been sucked to 27 kilometers around this ring, which you have to then clean up. And so it took a while to fix all those things. So what they did is they replaced some of the magnets. They had to replace some of the magnets. But they didn't. This is a picture of the magnet being lowered down that big shaft so that they can put it into where to replace one of the ones that broke. But they didn't replace them all, and that's because it would have taken probably a couple years to replace them all. They have to take they take the ring. It's in octants, and they have to warm the thing up to room temperature, and they fix whatever they're going to fix, and they have to cool it down. And the process of cooling it down takes months, and so they decided not to do that. And then some of them, some octants, they didn't even cool down completely or warm up completely. So once they knew what the problem was, they could measure the resistance between the magnets, and they could figure out where there was likely to be a problem. And based on that, they decided they could run, but not at the complete energy, at only half the energy that they had been designed to run at, without being in danger of having a problem happen again. So that's what they've been doing. And the reason they did that is that there's many things that you look for in particle physics which require the most energy possible, because you want to see the smallest things that you can see. But the Higgs particle, which I'm going to come to, is not one of those things. It's one of those things where you don't need a lot of energy to produce the Higgs particle. It was probably being produced all the time before the LHC was built. The hard thing about the Higgs is seeing it once it's been produced. And so they figured they could probably decide once and for all whether the Higgs particle is there before completely fixing it, and then they're going to shut it down and fix it. And then they're going to turn it on again at the full energies, and then hopefully they'll be able to benefit from having access to higher energies again than they've ever had access to before. So the plan has been that they've been running since 2009 at this half the energy that they were supposed to have. And they raised it up a little bit. They were running at 3.5 TeV, colliding with 3.5 TeV, so altogether there's 7 TeV available in the collision. They raised that to 4 on 4, so they'd have 8 in the collision last March. And they've been running like that, and they'll continue to run like that until Christmas or so. And then they switch into a mode where they accelerate heavy ions and not protons. And they'll do that until March 2013. And then they'll close it down, and they say it'll take until about 2015 to get it fixed, and then they'll turn it on again, and then we'll have it the way it was designed to be run. So that's the plan. And right now they're in the middle of this run, or they're getting towards the end of this run, where they're hoping to decide what's going on with the Higgs. So they've been running, and this was when they were setting a record, and it was not the most people in the control room. It was this is when they passed the highest energies that had been reached at other accelerators before them, and that was back in 2009. So they've been doing very well. The machine's been running very well, given that they broke it since then. So what were they looking for? So here I want to tell you about the Standard Model and why people expected there to be a Higgs particle, or Higgs boson. So first start off, I'll tell you about the Standard Model itself, and then I want to convince you that it really is a theory which worked very well. So I want to argue for you that it was very accurately tested, but in particular, you might have worried that if you're looking for a particle that has never been seen, you have to always worry that you're not going to have enough energy to produce it, and so that no matter how big a machine you make, you may not be able to find this new particle. And I've alluded to the fact that they thought that they could find the Higgs particle without being at their full energy. So that means they must have had some information as to how heavy the Higgs particle should have been. And I want to argue in this part of the talk, or tell you how it was that people had an idea how heavy the Higgs particle should have been based on the success of the Standard Model in describing the experiments that had been done. And then I want to finish off with why we don't think it's the right answer, the Standard Model, why we think it's wrong, but that'll be very quick, because I want to get to the Higgs. So the story in broad brushstrokes is you're looking at what things are made out of, and you're working your way down. And it's just a fact of life that nature comes to us in hierarchies of scale, that planets are bigger than people are bigger than molecules, and you work your way down to smaller and smaller things. And right now, the smallest things we know are electrons. As far as we know, electrons have no structure at all, which is to say that to the distances we've looked, you've never found a structure. That doesn't mean they can't have a structure. It just means that whatever the structure is, it has to be smaller than what we've looked. Things like protons and neutrons and atoms do have structure. Atoms are made of nuclei and electrons, and the nuclei themselves are made of protons and neutrons. It turns out that the protons and neutrons are made out of quarks and gluons. So there's 3 quarks for every proton. This here, I guess, is a neutron, 2 down quarks and an up quark. A proton would have been 2 up quarks and a down quark, and they're bound together by a strong force. And what they're asking in the LHC is, they're looking at, by going to higher energies, they're looking to smaller distances and asking, are they made of smaller things? And what are the basic players in nature? And they want to know what are the interactions through which they talk to one another. So the standard model, until recently, was our description of how all the particles that had been found related to one another, and what the particles were and what the forces were through which they interacted. It includes everything except for gravity. But you can include Einstein's theory of general relativity as our understanding of gravity, and you can combine them together to be the theory of everything that we know. Now, the standard model was invented by these 3 people. This is Sheldon Glashow, Abdus Salam, and Stephen Weinberg. And it was done in the 60s. So Glashow did his work in the early 60s, and then there was a pause because people were confused by something which the Higgs particle is the solution to. And then at the end, Salam and Weinberg, around 67, wrote down the kind of mature version of what the theory is. And it kind of evolved a little bit into the 70s, but it was, the basic idea was there in the late 60s. So the statement is that all the particles that we know seem to be built out of these things. So the green things are what I called hadrons. They're the things that take part in the strong interactions. The blue things are the leptons. They're the things that don't take part in the strong interactions. And the red things are the interactions. So the blue and the green things are what we would call matter. Those are the fermions. And the red things are the bosons, the things that mediate a force. So those are the categories I was talking about earlier. So everything we see in nature around us is in the first column here. The up and the down quarks, they assemble into protons and neutrons, and those make nuclei for atoms. And then the electrons combine with those to give us atoms. Here's the neutrinos. This row here is the neutrinos. The neutrinos, we know that they're produced they're not in atoms, but they're produced in radioactive decays, and so in nuclear reactions. And so the ones that come from the sun, for instance, are being produced by the fusion of hydrogen into helium in the sun. Now, one of the things that's interesting about the standard model, which no one really understands, is that everything we needed to understand nature around us is in this first column, but there's 2 more columns, and basically everybody in these columns is the same as the one to their left, but heavier. And so there's a heavy electron, which is the muon, the one I talked about that kind of goes through the detectors, and you actually have to have detectors on the outside to see them going through. But it's exactly like an electron, except it's heavier. And the only difference is that it's heavier. And there's also another that's heavier still, called the tau lepton, which is like a muon or an electron, which is just even heavier than the muon was. And there's three neutrinos in the same way. There's 3 copies of the down quark and 3 copies of the up quark. And there's really no understanding as to why we need 3 of everything. But we do. All those particles have been seen. And the forces through which they interact are governed by the photon, which is describing electromagnetism, the gluon, which is the thing that is describing the strong force, the thing that holds the nuclei together and holds the quarks into the gluon, into the protons and neutrons. And then the W and the Z bosons are describing the weak interactions, which are the ones that are responsible for radioactive decays, and so through which we found things like the neutrino. And those are the particles that have been seen until, I have to change the slide now because there's now a new particle that's been discovered just this past July. And it's very tempting to associate it with the particle that was missing. What I'm showing you here is the particles that have been seen experimentally until last July. But it's not the standard model. The standard model had these particles and one more, the Higgs boson. And so, of course, everybody's expecting, everyone was looking for this extra particle the standard model predicted should be there. And we found a particle, and everyone's asking now, is that the particle we were looking for? So what I need to do now is to motivate for you why people weren't happy just to have the particles we've seen. Why did they need the Higgs particle? And that was kind of what the delay was between Glashow and Weinberg and Salam in understanding what this theory was. The Higgs boson is there to solve a problem that you have if you don't have the Higgs boson. And it took a while for people to figure out what was going on there. And it's a very deep theoretical picture as to what's going on in the vacuum, but one for which we had no experimental evidence really until now, if this is the Higgs boson that's been discovered. So let me set up the problem that the Higgs particle is supposed to solve for you. So what you should know is that these particles, the hadrons and the leptons, the things that are the fermions, the things that matter is made out of, they come to you, they have spin. And so it's very much like the spin of a photon, the polarization of light. When you wear polarized glasses, the reason that you filter out some of the light is that light comes in two spins, and the polarization is allowing one of them through, and the other one doesn't get through, and that's why you get less glare, say. But it's true for all these particles that they all have two spins like that. You can think of it very much the same way. And they're called left-handed and right-handed in the sense that if the particle had been moving in that direction and it's spinning that way, that would be right-handed. So if your thumb is the direction of motion, that's the spin is what your fingers are doing. And so the left-handed would be going that way, and right-handed would be spinning that way. And so that's the label. That's a way of labeling the spins that these particles have. So that's not a puzzle in itself. That's just a fact. Now, the interesting thing is that in the 60s, people realized that there's an experimental fact about the weak interactions, the ones that involve radioactive decays, which relates to the spins of the particles involved. So an example of a weak interaction would be a process where a muon, the heavy electron, decays into an electron down here on the right and two neutrinos. And it does it by emitting a W particle, which then decays into an electron and an anti-neutrino, it turns out. But that process, the things involved here, the muon and the electron and the neutrinos, they all have spin. And this experimental fact is that this reaction, the experimentalists can measure the spins involved by looking at the distributions. When the muon decays, what fraction of the time does the electron go that way versus that way compared to the neutrinos? Say, by measuring the distribution of how things come out of a decay, you can figure out the spins of the particles that were involved in the process. And in the 50s, many experiments led to the conclusion that the weak interactions only involve left-handed particles. They don't involve right-handed particles. And that was just an experimental fact. And Glashow, when he was writing his theory down, built in that experimental fact. So it's not a prediction of the Standard Model. It's just a fact that was built into the construction of the Standard Model. Now, that in itself isn't a problem. It's just, again, expressing what seemed to be a fact. Now, the puzzle is that the way I've described handedness to you, you should have been suspicious, because if I told you that something was right-handed, I said that the particle is moving that way, and it's spinning that way, and so that's why it's right-handed. But you could have said, well, that's fine, but let's say I run past the particle, so I'm moving faster than it is, then as far as I'm concerned, it's actually going that way. But it's still spinning that way. So if you thought it was right-handed, and I'm running past it faster than it is moving, then I will think that it's left-handed, because I think its direction of motion has changed, but its spin hasn't changed. And that's true. The way I'm describing handedness really only makes sense if you can't catch the particle. So it would make sense if it was moving at the speed of light, because no one could go faster than the speed of light. You can never catch somebody moving at the speed of light. So particles like photons can have a handedness. That's the polarization that you see in sunglasses. But it shouldn't be true that the handedness, the way I'm describing it, makes sense for something which is moving slower than the speed of light. So it shouldn't make sense that the weak interactions could only care about left-handed particles, because that should only have made sense if the particles were moving at the speed of light. But we know the electrons don't, and the electrons were part of that decay that I showed you. Another way of saying that is that when something moves at the speed of light, we say it's massless. If something's not moving at the speed of light, you can catch it, and you can make it sit still next to you, and then the energy that it has, we call its mass, so it's massive. You can never do that with a photon because you can never catch it. So another way of saying things had to be moving at the speed of light is that they had to be massless. And so the puzzle was, it seemed like our understanding of the weak interactions implied that all the particles involved had to be massless. And we know that the electron has a mass. We know that the muon has a mass. They don't move at the speed of light. They move at some speed less than light. So that was the puzzle. And the Higgs particle, the Higgs mechanism, was the resolution, is our current understanding of the resolution of that puzzle. And the Higgs mechanism was invented by all these people. Peter Higgs is the guy on the left, but this is Braut, Engler, Anderson, Kibble, Guralnik, and Hagen. So there's going to be an interesting mud fight to see who gets the Nobel Prize if they've actually found the Higgs boson, because only 3 of these people can get the Nobel Prize. That's one of the rules of the Nobel Prize. And so Higgs will certainly get it, I think, but then it's up for grabs who the other 2 are. My vote is it'll be these 2. Well, one of these guys actually died recently, but it's Engler and possibly someone else. So what is the Higgs mechanism? So what is it? How do you reconcile this basic problem that people had in the 60s, understanding particle physics? Well, the picture that they had, so the way that they come up with a solution to the problem is that they rephrase the problem as a symmetry problem. That the weak interactions have a symmetry. Actually, let me not say it that way. A better way to say it is that when you see a particle, we always think that it's in isolation if it's an elementary particle. And that's because we're trained to think of the vacuum, the thing that you would have had without the particle, as being the absence of everything, but not to have any physical properties itself. And so the observation that Higgs and company made was that needn't be true. The way a physicist, strictly speaking, a physicist thinks about the vacuum as being the thing with the lowest energy. And normally that's the same thing as you would have thought the first way I described it. If particles have energy and you remove them all, then you've got the lowest energy. And the thing that took a while to sink in was that's often true, but it needn't be true, that the absence of all particles and the absence of all things is the thing with the least energy. What Higgs and company did is they proposed a force, a field, which, like the electromagnetic field, it's sourced by particles. If you give me a charged particle, I'll have an electric field. If you give me a massive particle, I'll have the Higgs field. It'll be a force, it's a boson, it's something which is a force set up by particles. But the interesting thing about the Higgs particle is that, unlike the electric field, if you remove all the sources, it actually costs you less energy to have the field than not to have the field. So even in the absence of particles, you can still have the Higgs field. And so if that's true, that would mean that the vacuum is like a physical thing. It has properties. It's like an object that if you perturb it, you should be able to set up waves in that object. If you heat it up, then you should be able to change the properties of that object. And so the observation they made was that the vacuum can have physical properties, and in particular, if you're asking how fast something moves or what its mass is, you shouldn't ask it in isolation. You have to ask it in the context that it's moving through this vacuum, which has physical properties. If we had been living in water, we wouldn't have been surprised to know that different things will move through water with different speeds. Because if you didn't know the water was there, you might have had a puzzle understanding why fish and gorillas don't move through water at the same speed. But if you know about water and you know about resistance, then you'll know that there's something to be understood. I don't want you to think that this is literally what's going on with particles in the vacuum, because this makes it sound like it's friction, and it's not friction. So the particles are not slower moving through the vacuum because they're slowed down by the friction of the vacuum. And so then they should eventually stop. That's not what's going on. It's more that particles are moving through the vacuum, and they have an energy of interaction with the vacuum, and energy and mass are the same thing as far as Einstein's concerned. And so what's really an energy of interaction with the vacuum, if you didn't know the vacuum was there, you'd think that's a mass, because mass to a physicist is the energy that something has when all the other things that would have had energy are gone. So if there's no energy of interaction, there's no energy of motion, the energy of just sitting there is what we would call the mass of a particle. But if you didn't know the vacuum was there, an interaction energy with the vacuum you'd also think was the mass of a particle. So the Higgs observation is that if you understand that the vacuum can have properties, what you're thinking of as a mass is really an interaction energy with the vacuum, and that removes the consistency problem that they had between the understanding the weak interactions and the ability of particles to move at less than the speed of light. If you hadn't had physical properties in the vacuum, they would have been moving at the speed of light. But the vacuum is changing those properties and giving you an energy of interaction, and that's why they can have a mass, even though they take part in the weak interactions. So the way you test that theory, the acid test for a theory like that is, if you perturb the vacuum, if it has properties, you can perturb it. Nothing can go faster than light, so if I perturb it over here, you won't know until at least the time for light to travel from me to you takes place. So there should be waves in the vacuum that tell you about how you perturb the vacuum. In the same way that Einstein says that there's waves in space-time. If you perturb stress energy, or if you move masses around, the space-time itself has to have waves, because nothing can travel instantaneously. It has to get from wherever you did the moving to wherever you see the results of the moving at most at the speed of light. So something has to carry the news of the motion through space-time or through the vacuum. So there have to be waves in the vacuum if the vacuum has physical properties. And in the same sense that photons are the particles that are associated with waves in the electromagnetic field, Higgs particles are the particles associated with waves in the Higgs field. So if you lived in water, the acid test that the water was there would be, sure, you move particles through the water, they move differently, but the water itself should have a wave. And if you find that, then that's the acid test that the water is there. The Higgs boson is the acid test that the vacuum has properties. And so looking for the Higgs boson is looking for a wave, and you want to perturb the vacuum in such a collide particles so violently that you perturb the vacuum and you see a wave in the vacuum, or the quanta of that wave, which is the Higgs particle. So just to summarize, the problem was the weak interactions seem to require things to move at the speed of light. The only way we know how to understand that still now, 30 years later, is if the vacuum has properties. The Standard Model has a particular theory of how those properties might look. But in all the alternatives to the Standard Model, it's also true that they give the vacuum properties, and they have different predictions as to how the vacuum might look, but they all rely on the vacuum having properties. So it's a very deep statement about the vacuum that was made in the 60s, and for which we've had no experimental evidence at all until this summer, hopefully. So now why would you believe a picture like that? It sounds very fishy. Here's just a cartoon to show you that we're not all nuts. So this is a graph of the probability of taking electrons and positrons, the anti-electrons, and colliding them, and you produce particles, all kinds of particles. In this case, they're following hadrons, which are the particles that take part in the strong interactions. And this is showing you the likelihood of that collision to happen as a function of the energy with which the collision happens. And you see that there's a theoretical prediction, which is this nice black curve. That's what the Standard Model predicts. And all these dots are various experiments that have been done over the years. Different colors are different experiments in different places in the world. The red ones were done in the same tunnel that the LHC is in now. It was a previous experiment that used to be there. And so it works really, really well. And it works to an accuracy of less than 1%, fractions of a percent. And there's only a couple parameters that go into that prediction. And there's many, many more data points than you have parameters. And in particular, that success tells you something about the Higgs particle, because the mass, what you don't know so far from what I told you about the vacuum is how much energy it costs to set up a wave in the vacuum, because that is what you'll need to know if you're going to produce a Higgs particle. So I want to tell you now how you can figure out in advance, how people knew already before they found it, what the Higgs particle mass had to be. And the way they did that is that they used the W boson, which is another particle. In the Standard Model, you get to predict the value of the W boson mass. It's not something that you use as a parameter. And so this is showing you a plot of the units here are GeV. GeV is roughly the energy that you would get by taking a proton and turning its mass into energy. The yellow strip here is showing you the measured mass of the W boson. And the blue strip is the prediction in the Standard Model of the W boson mass as a function of the Higgs mass. So the Higgs mass, the Higgs particle mass is here, and it's the same units. This is 100 GeV. This is 80 GeV is the mass of the W boson. Here's 1,000 GeV. This is a logarithmic scale. So it depends very, very, very weakly on the Higgs mass, but it does depend on the Higgs mass, and they agree down here, but they only agree down here. So the Standard Model could only get the W boson mass right if the Higgs mass was light. And how light? It had to be 100, maybe 200, but not much more than that, GeV. They found it at 125 GeV. The thing they found, which we hope is the Higgs particle, is 125 GeV. And so they knew that if the Higgs particle, if the vacuum was described by the Standard Model, whatever the wave is, it can't be too heavy because of an argument like this. So why don't we believe the Standard Model? It sounds like it's a great model. Well, it's two things it gets wrong, at least two things, but the main things it gets wrong, the experimental things it gets wrong are, I told you that neutrinos come to us from the sun, but there's a long-standing problem in understanding that, because people have been trying to measure these neutrinos. They're hard to measure. They go through us all the time. We don't see them. But you can eventually find them. The way they find them is they make tanks of water, or tanks of cleaning fluid. They put it in mines underground so that there's not any radioactivity coming from the cosmic rays in space. And they look for, every once in a while, a neutrino goes through and it causes a reaction in the chlorine in that tank. And maybe once a month, it might produce 1 atom of argon. So after 6 months, you're expecting 6 atoms. So they flush the tank and they count the atoms, the argon atoms, and they get 8, or they get 3, plus or minus 2. So they get 3, not 10. And so no one believed them for 30 years, because no one believed that you could count atoms that well. But so they do it again with germanium, and they do it again with something else. They do it in water. And then what emerged over many years was they were counting them right. They were measuring how many neutrinos there were, and it was almost right. They were getting about 1/3 of what they thought they should be getting from the sun. You know how many should be coming because you know how bright the sun is. So you know how many nuclear reactions are happening, and so you know how many neutrinos should be coming out. And so they were getting only about 1/3 as many as they should be getting. Turns out what's going on is that they were only expecting one type of these. There's 3 neutrinos, remember? There's 3 copies of everything. They were only expecting one of those types to come from the sun because it's the nuclear reaction involving neutrons and protons. It's in the first column. So standard model says you should only be getting the one, so that's all they look for. Until in Sudbury, if you've heard of the Sudbury Neutrino Observatory, they built the detector down there that can see all three kinds of neutrinos, and lo and behold, they found a third of what they should have seen in the one that they were looking for, but the other two were there, even though they shouldn't have been there, and if you add them all up, you got what you should have gotten from what the sun was supposed to be shining. So the standard model doesn't describe that. It says that you should only be getting one of these things, and so that's something with the standard model just getting wrong, and so you have to fix that. Another thing that you get wrong is cosmology, because cosmology is extremely successful these days. It's a really good cosmological model. The theory of the universe as a whole has been tested very well by observations of the universe as a whole. And one of the amazing things in the last 20 years is that you can now measure the energy density in the universe by measuring how the universe behaves, because you can measure how it gravitates. And by measuring how it gravitates, you can figure out, using Einstein's theory of relativity, what's out there, even if you don't see it. And the short version is that there's two kinds of things out there that we don't understand, dark matter and dark energy. This is the pie chart of the universe, that 75% of what's out there is dark energy and 21% is dark matter. And 4% is what's in the standard model, that red slice. All the atoms you've ever heard about in university or college or school are there. And I think that we should give that to the chemists. And now physics is supposed to figure out what this stuff is, the blue and green stuff. And so whatever it is, it's not the standard model. And so there's something going on there that we have to replace the standard model to understand. So we're pretty sure that it's wrong, the standard model. It gets a lot of things right, but there's a couple things it's getting wrong, and so it's got to be replaced. And so the LHC is hoping to see what the new theory is that replaces it, to find more ways in which it's wrong, enough ways that we can figure out what's right. So what do they see? So I'm kind of coming to the end here. They say they found something, and so is it the Higgs? You know, why do they think they found something, and why, how would you know if it's the Higgs or not? So let me tell you first how you'd look for the Higgs and then what they say they saw. So here's an example of what they think is a process. Again, you have protons colliding in a detector. This is a cartoon. This is now the CMS detector. This is a readout of what their detector saw. It's got two things coming out here, which are photons, and they think what happened in here, there's a lot of other things going on, which is just junk. Protons are made of a lot of things, and mostly when you collide, there's a lot of other stuff going on too. So they think what happened is that they produced a Higgs particle which decayed immediately, and they didn't see the Higgs particle, but they saw it decay into two photons. So if you're looking for the Higgs particle, you have to first know what's it decay into. And the answer to that is coming from the fact that you know why it's there. It's there to explain why masses are there. If you thought about, before I say that, sorry, there's one more thing I wanted to say. You might have said, there's a needle in the haystack problem here. If they think they saw this was supposed to be the Higgs producing two photons, there's a lot of things that produce photons. Anything with electric charge produces photons. So how do you tell the Higgs producing photons from anything else producing photons? And that's a good question. That's something that's what's actually taken so long in seeing the Higgs. If you see two photons coming out once, you actually don't know if that was the Higgs or not. The way you tell if the Higgs is there is you do it over and over and over and over again. And then the way you tell if two photons came from the Higgs statistically is that if two photons come from the decay of the Higgs particle, they'll have a special property, that if they came from the decay of a Higgs particle, if the Higgs particle was sitting here at rest, when it decays, momentum conservation will make the photons have to come out in opposite directions exactly, and then energy conservation will make their energies add up to the mass of the Higgs particle, times c squared. And so because their momenta are equal and opposite, their energies have to be equal, and so they'll have exactly half the mass of the Higgs particle in energy, every time. Of course, when you get these photons coming out of the detector, they're not coming out back to back, they're coming out in some random direction. So what you do is you imagine if I was moving in a frame in which the photons were going in opposite directions, and that would have been the frame in which the Higgs particle was moving. I'd be then, if I'm in a frame where the photons are going back to back, and if they came from a decay of a Higgs particle, then I'm in the rest frame of the Higgs particle. In that frame, they should always have the same energy. So what you do is you take the energy of these two photons, and you go to this frame where they're moving in opposite directions, and you ask what's their energy, and you plot the number of times they have a given energy as a function, as a graph. And that's what this graph is here. This is the number of times they see two photons having a given energy, and then this is not the energy of the photons. This is the energy of the photons in the frame where they were moving in opposite directions. So in that frame, the way they've plotted, all the photons coming from the decay of a Higgs should always have the same value. And so in this particular plot, here they've simulated what they would see if they had a Higgs being produced with 130 GeV. Again, the units are 1 GeV is roughly the mass of a proton. And this is what they actually see. This is a measurement of the photons they see. They see photons coming from everything. And they didn't have at that time any particular evidence that there's anything special going on in any one place. But the way so to summarize, to see that the Higgs has produced 2 photons, you do it over and over and over and over and over again. If you see 10 million pairs of photons, and 3 of them happen to all add up to 1 energy, then you're not convinced because that could be a statistical fluctuation. But if you have 10 million photons, pairs of photons, and 5 million of them are all in the same energy, that looks like the decay of a particle, because that would be very, very unlikely to happen randomly. So now they go look, but maybe it doesn't go into photons. Maybe it goes into something else. So what does it go into? Actually, I'm not going to show you that slide. So this is what they saw. This is the same thing I was talking about. This is the number of times 2 photons came out, and this is against the mass of the 2 photons, which is the energy in the frame where they're going in opposite directions. And now you see what's happened is that there's a bump there. So there's a statistically significant occurrence where you're getting 2 photons from the decay of something. And that something, you can tell its mass because it's the energy with which the photons are coming out. You know, the photons each have half the mass, and so you can figure out what when you add them together, the 2 masses add up to the mass of the thing decaying. So whatever it is, that thing is decaying at about 125 GeV. So it's about 125 times more massive than a proton is. So that's the big news. They see something going into 2 photons. So that tells you something right away. Photons are bosons. The only way you can get 2 bosons is from another boson. So whatever the thing is that decayed, it can't be a fermion. It's got to be a boson. So it's a mediator of a force. Photons, we know, have a spin, and we know what the spin is. So you can ask, if something decays into 2 things with the spin of a photon, what's its spin got to be? And there's 2 answers. It's either 0 or 2. The Higgs particle is supposed to have spin 0, so that's good because it's something which the Higgs particle could do. Photons don't carry electric charge. Charge is conserved, so if something decays into them, that thing had to be neutral. That's good. The Higgs particle should have been neutral. And we know its mass because we know where these photons, what the energies were when they came out. So you can take to the bank that they've seen something this summer decay into 2 photons, and it has those properties. And the question is that the Higgs particle? How would you tell? Well, the standard model tells you everything there is to know about this Higgs particle. It tells you that it decays into 2 photons. It tells you how often it decays into 2 photons. In that previous plot, I showed you a simulation of how often it would go into 2 photons if it had a mass of 130 GeV. How did they know that? It's because the standard model told them what the answer would be if you knew what the mass was. But it also decays into other things. It could decay into 2 bottom quarks, or a bottom quark and an anti-bottom quark, or into 2 Z particles. Or it depends on what the mass is, what it decays into. And in particular, if you think about why the Higgs particle is there, it's there to give particles mass. It's a wave in the vacuum. If you think of a particle moving through the vacuum, you can think of it getting a mass because it's interacting with the Higgs field, the thing that's in the vacuum that gives you mass. But that same picture, if you read it going from bottom to top, describes the decay of a Higgs particle. So the Higgs particle will decay into pairs of particles. And the probability of it to happen is controlled by the same thing that's controlling the mass of the particle that is being decayed into. So that tells you that, if you work it out in detail, that the likelihood of a Higgs decaying into a particular particle will be proportional to its mass squared, it turns out. And so the Higgs will like to decay into the heaviest thing it possibly can decay into that's lighter than itself. It can't decay into something heavier than itself and still conserve energy, but it can decay into things lighter than itself. And it'll find the heaviest one that it can, and it'll like to decay into that. So that's what the standard model Higgs should do. And so now you look at all the decays of the Higgs that you should see, and the standard model tells you that if you've seen this many decays to photons, you should see this many decays into this and this many decays into that, and check if that's what the standard model says it should do. So this is a plot showing you what I just said. This is as a function of the mass of the Higgs in the bottom here, and the pink area is where they think they found it. This is the fraction of times the Higgs particle decays into things. So this is the fraction of times it decays into bottom quarks and anti-bottom quarks. And this is 100% of the time, that's 10% of the time, that's 1% of the time. So when it's light, it loves to go into bottom quarks. But then when it's heavy enough, it eventually likes to go into W bosons and Z bosons because it's now heavy enough that it can decay into those. And where the thing was found is in here. So it likes to decay mostly into bottom quarks, but it also likes to go into W bosons and it likes to go into tau leptons. And way down here is the photons. You might worry, photons actually don't have a mass. They move at the speed of light. Why does the Higgs talk to it at all? So if you ask me that, I can tell you that later on, but it happens, and that's the one that they found it with. But these other things should be more common than what they actually saw for the photons. So now what do they see? So this is a picture of the Higgs being produced and decaying into, what they actually do is they collide protons and they look for 4 leptons to come out. So that could be 4 electrons or 2 muons and 2 electrons. And so what you're supposed to see here is that the blue thing is what you would have expected to see if everything but in the Standard Model was there except for the Higgs particle. And so this thing here on the big blue spike is to do with things that have nothing to do with the Higgs particle. But the thing over here in the middle is the evidence for the Higgs particle. You can't see in the scale on the bottom here, but that's happening at the right mass for 126 GeV. And it's above this blue area, which is as high as you would be allowed to go if you did not have a Higgs particle in the Standard Model. And so they have evidence that the Higgs is decaying into other things, in particular into Z and two Z particles, and the Z particles then decay into electrons and muons. And so this is coming in at a rate which is where it should come in if it had been the Standard Model particle. This is a plot which is just showing you that if you combine all the things that they see and you ask the question, is it likely that what they've seen is just some random fluctuation, they haven't really not seen any particles at all, then that was a very convoluted way to say it. You could ask, what's the likelihood that, since they're making a statistical argument, they're saying if I see a pair of photons coming out, I'm arguing the Higgs is there because of some statistical argument. If you ask the probability of them to have being fooled, and thinking that the Higgs particle is there and have it not really be there, this graph is showing you the probability of that being true, and it's basically 1 in 3.5 million. So they normally ask for a 5 sigma statistical significance before they claim a discovery, and that's what they found. So, is it the Higgs? We don't know. But it looks like a duck, it smells like a duck, it walks like a duck. It's probably a duck. And so the state of the art now is that this thing has the properties that you would expect it to have if it was the Higgs particle, the Standard Model Higgs particle. But not all things that look like ducks are ducks, so you should keep your eye on them. And the important thing is that they're still collecting data, and they're going to know they don't shut down until Christmas. They're going to announce something in November as to they're going to analyze more data that they've been collecting since July, and then they're going to continue analyzing things, and there's another conference that happens in February. Watch the news stories, because if this thing continues to look like the Standard Model Higgs particle, they're going to know much more about it, because all the error bars are going to get smaller because they'll have accumulated many more events. If it starts to look different from the Standard Model, and there's a couple places where there's hints of it looking a little bit different from the Standard Model. There's a little bit too many photons and a little bit too few tau leptons. If that is borne out with smaller errors, that'll be the first sign that it's not the Standard Model Higgs particle. Probably it's some other kind of Higgs particle, but it's it's something in the vacuum, but it's not the Standard Model way of describing the vacuum. But we're going to likely know in the next 6 months, one way or another, certainly much better than we know now. Here's where I would give you the implications, and I'm going to just flash through this because I'm out of time. The short version of this is that there's 3 categories of theories that have been proposed to replace the Standard Model. And they each have a statement about what the Higgs should look like and how likely it should decay into various things. And I want to show you how happy these people are given what they've seen about the Higgs. So there's 3 categories. The first category is the historically conservative category. Everything's made of smaller things, and in particular the Higgs might be made of smaller things. If that were true, you would not expect it to go into W's and Z bosons, or Z bosons, which they've seen. So most people, I think, feel that this is actually coming, it's on its dying legs. There's hardcore people, I think, that will stick to this one for a while, but these people are not happy people because they're not seeing what they expected the Higgs to look like. The thing you've probably heard about as being the most popular option is the supersymmetric option, where every particle we know has a friend who's if the particle we knew was a fermion, there's a particle that's related to it, which is a boson. And if the particles we know that are bosons, they have particles related to them that are fermions. And there's a theory of supersymmetry that predicts that. They're also not very happy, partly because of these partners that they expected to see they haven't seen. But on top of that, the theories predict the Higgs particle should be light, and it's not as light as it's expected to be. It's not impossible to get it as heavy as what's been found, but it's not what the theory likes to do. So people start to feel like they're pushing the theory in a direction it didn't want to go. So they're also not very happy campers. I'm giving you a completely unbiased opinion here. The third category is the one that I believe in. So, so this is the picture where the LHC is where there's extra dimensions, and gravity is actually going to be important in the Large Hadron Collider. In this kind of a picture, the thing that you would expect is the Higgs will look like a Standard Model Higgs. It's not going to look very exciting. And so I'm a happy camper. And so if you remember nothing else from this talk, remember this, that I'm a happy camper, and that if this turns out to be right, I told you first. So what's the bottom line? The bottom line is the first bottom line is that the LHC was, we've been told for 20 years it's going to change the way we think about the foundations of what matter is made out of and how it interacts. And it's already doing that. In some ways, it's a disappointment. We had hoped that by now we would know more, we would have found more particles that were different from the Standard Model. And it might be that all we've seen is the Higgs particle, which the Standard Model expected to be there anyway. Part of the problem there is that the theories that differ from the Standard Model, you typically require more energy to test them. The reactions that they would predict that the Standard Model does not have, the likelihood of them happening grows with energy. So the higher the energy you have, the more likely it is you'll see them. And it's hard to fight that if you don't have enough energy. So what's been hurting them is the breaking of the LHC. They're not running at their full energy. Once they get to their full energy, that'll be the time when you can decide if you're disappointed or not in what they found. And if they're going to find something, for instance, if they find nothing, will be disappointed because the slide, my happy face slide, will become a sad face slide, that they really should be seeing things. But the acid test is not until then because of the fact that it broke. So you shouldn't feel that it's been a disappointment already because they haven't really had a chance to test things perfectly yet because they haven't had the machine running at its full energy yet. But it is changing. Many things that people thought were possibilities are now being disfavored. And that's also good because that means you can start crossing things off your list. That supersymmetry, I personally think, is what you would call a Teflon theory. It's a theory that has it's been unhurt so far, surprisingly so, by the lack of evidence for it. And so I think it's about to face a brutal death, and the LHC will be the thing that does it to you. And everybody in the end of the day will be happy by that because we learn something when a theory dies or when a theory succeeds. The second thing is they found something. It may not be the Higgs, it may not be the Standard Model Higgs, but there's a new elementary particle in the world, which is a boson. There's a force we did not know about before. We suspected strongly there had to be something like this, but it is there, and now we know where it is. It's at 125 GeV. We know it decays into 2 photons. It decays into pairs of Z particles and into leptons. And so it looks like a Standard Model Higgs. It may be a Standard Model Higgs. It may not be a Standard Model Higgs. It might be close to one, but not exactly one. And we're going to find that out sooner because you don't need energy to find that. You need lots of events, which they're going to do. They're accumulating that as we speak. The third thing is that this Higgs mechanism, if it is the Higgs, Standard Model or not, that's telling you something. If that's all they find, that's not a disappointment because there's a very deep statement being made about the vacuum. It's not empty. It's full of stuff. And it's something which all theoretical physicists believed for decades because we had no other way of understanding the interactions that we see. But you're never quite as happy as when you have experimental evidence for an idea like that, especially a foundational idea like that. So this picture that the vacuum has properties seems like it's true. If this is a Higgs or the Higgs, what we're probably seeing there, it smells like what we're seeing there, is a wave in the vacuum. And that's a phenomenal thing, that this theoretical limb we've been out on about the vacuum having properties now has evidence supporting it. But what we're really hoping for is a surprise. That the best thing would be that everything I've told you is wrong and something happens completely out of left field because that's when you really learn the most. And we can only hope. Don't bet your money until, don't pay off your bets until they're running at full energies, which will be 2015. But I think it'll be very exciting. And I hope you'll all take part and follow along. So thank you for coming out tonight.